Welcome, everyone. Today I will be sharing our latest work at the National Center for High-Performance Computing. We are exploring the intersection of big data, high-performance computing, and AI agents to drive biomedical innovation. Our focus will be on how these advanced technologies come together to completely revolutionize complex scientific workflows. Our core concept is agentic HPC, specifically applied here to autonomous 16S rRNA microbiome analysis. Imagine a completely automated pipeline extending from the researcher's initial target to the final scientific report. By utilizing an AI agent workflow controller connected to local large language models, we can securely orchestrate Chime2 tasks to generate reproducible, high-quality biological insights. Traditionally, scientific workflows rely heavily on fragile, manual execution. Researchers spend countless hours writing scripts, troubleshooting logs, and adjusting parameters. Agentic HPC changes this paradigm. Instead of manually operating tools, a researcher simply defines a goal. The AI agent seamlessly interacts with the HPC infrastructure to plan, execute, and adapt the workflow to generate the final results. We chose 16S rRNA analysis as a stress test because it demands both rigorous computational execution and nuanced biological interpretation. From importing raw reads to performing DADA2 denoising and calculating diversity metrics, the agent must navigate multiple key decision points. It traces the provenance of every artifact, ensuring that the resulting biological insights remain highly reproducible and auditable. But the real question is whether an agent can recover from real-world workflow friction. A truly useful scientific agent must autonomously plan, execute, diagnose errors, and revise its approach. In a live environment, it will encounter outdated parameters, version mismatches, and strict privacy constraints. Overcoming these hurdles is essential for maintaining a reliable workflow within a secure data boundary. To answer this, our proof of concept evaluated 4 critical dimensions: autonomy, consistency, privacy, and scientific meaning. We investigated whether the agent could run a complete Chime2 workflow without human intervention, maintain performance across different deployment architectures, successfully correct script failures, and keep sensitive data entirely within an air-gapped sandbox while still producing biologically coherent outputs. We tested the exact same microbiome workflow across 3 distinct agent architectures using different inference backends. The first utilized a cloud-connected Anthropic API. The second and third were entirely local, leveraging self-hosted Minimax and the internal NVIDIA Nematron API. Regardless of the underlying inference model, the biological task remains identical, allowing us to evaluate the impact of different security configurations. For biomedical data, security is paramount. Our air-gapped sandbox ensures that data, tools, inference, and results never leave the HPC environment. We built a 5-layer architecture integrating input data, HPC execution, local LLM inference, agent orchestration, and bioinformatics tools. With external telemetry disabled and internet access blocked, everything required to generate a scientific report stays strictly internal. The agents successfully converted a single high-level goal into a complete Chime2 run. Throughout this process, the agent assumed responsibilities typically handled by human researchers: checking inputs, writing scripts, parsing Slurm logs, diagnosing issues, and verifying outputs. Whether using external APIs or our secure local models, the agents demonstrated remarkable autonomy in both workflow planning and error correction. Crucially, all 3 agents completed the workflow and reproduced the exact same biological patterns. Processing our 34-sample dataset, they accurately identified the dominant taxonomy and generated consistent beta diversity plots. The results clearly clustered samples by body site, showing a strong distinction between gut microbiome, tongue, and palm microbiome, which perfectly validates the scientific viability of our approach. Ultimately, agentic HPC shifts the user experience from tedious command execution to focusing on scientific intent. It delivers scientific validity, operational efficiency, and strict privacy. However, it does not replace the researcher. By providing an auditable preliminary analysis with complete provenance, the agent empowers domain experts to spend their time on human-in-the-loop review, biological interpretation, and high-level decision-making. Moving forward, our next step is a controlled benchmark with much stronger guardrails. This initial proof of concept successfully proved feasibility, but we recognize its limitations regarding dataset size. Our roadmap spans short-term validation, comprehensive benchmarking, and eventually secure production scaling. To achieve this, we will implement strict approval checkpoints, offline mirrors, and signed containers to further harden the environment. In summary, agentic HPC transforms a secure compute cluster into an autonomous scientific workbench. The researcher defines the high-level goals. The agent then plans, executes, and validates the entire workflow within a strictly air-gapped boundary. Finally, the domain expert reviews the generated artifacts and reports. This powerful synergy ensures biological validity while drastically accelerating the pace of modern discovery. As we continue to refine this intersection of AI and high-performance computing, we are actively laying the foundation for faster, more secure, and highly reproducible biomedical research. The transition to autonomous scientific workflows marks a significant leap forward for our field, and we look forward to exploring these new technological frontiers with all of you.